Hi, everyone. In this video, I want to quickly give a summary of each of the convergence tests we've discussed thus far. In particular, we'll briefly review each of the specific tests that we've discussed, and we'll discuss strategies for picking out the most appropriate convergence test for a given series. So to begin with, let's quickly step through each of the different tests we've seen for series. So the very first type of series we discussed were geometric series. And we saw that if we have a geometric series, so that's a series of the form a times r to the n, it converges if r is less than 1 and diverges if r is greater than or equal to 1. So if we have a geometric series, very easy to determine convergence or divergence solely based on the value of that ratio r. We then learned the nth term test, or the test for divergence. That gave us a way of concluding that a series diverged if the limit of the terms was non-zero. So again, we could sort of just look at a series. If the limit of the terms was not zero, then the series must diverge. But if the limit of the terms was zero, this test doesn't tell us anything. We can never conclude convergence from this test. We then discussed the integral test, which relates convergence or divergence of a series to convergence or divergence of an improper integral of a related function. So we saw how to construct this related function f, and then we could look at the improper integral of f from 1 to infinity, and basically see that it behaves the same as the series a sub n. So if the improper integral converges, then the series converges. If the improper integral diverges, then the series diverges. Again, this was limited to series which have all positive terms. So again, this is sort of a restricted test, but when it does work, it's very useful. From that integral test, we were then able to come up with the p-test for series. So the p-series, which is a series of the form 1 over n to the p, converges if p is greater than 1 and diverges if p is less than or equal to 1. So again, this was just sort of a quick way to check for a very specific type of series whether or not the series converged. We then switched over to some comparison tests. So two types of comparison tests. The first was just the comparison test, sometimes referred to as the direct comparison test. In that case, if we have two series, both of which have non-negative terms, and where you know that the terms of one series are greater than or equal to the terms of another series, of the other series for all n beyond some certain value, then if the larger series converged, then the smaller series had to converge. And if the smaller series diverged, then the larger series had to also diverge. So again, this is where we had the balloon analogy, right? If the smaller balloon pops, then the bigger balloon must also have popped. If the larger balloon did not pop, then the smaller balloon did not pop. However, there are sort of some restrictions here. The first is that if you're looking at two things and you see, for example, that the smaller series converges, that doesn't tell you anything about whether or not the bigger series converges. If you see that the bigger series diverges, that doesn't tell you anything about whether the smaller series converges or diverges. So it sort of doesn't work in every case. You have to have the right setup. And in practical terms, like actually verifying that these inequalities hold and finding the right thing to compare a series to can be quite tricky in some cases. We then looked at the limit comparison test. The sort of advantage of the limit comparison test being I didn't need to establish that inequality. And so for the limit comparison test, I just needed two series with non-negative terms. I look at the ratio of those terms and then take of the nth terms and take a limit as n goes to infinity. If the value that I get when I take that limit is greater than 0 and is some finite number, then the two series have to behave the same. So either they both converge or they both diverge. Now again, sort of some limitations here. One obvious one is that that limit could be 0 or could be infinite, in which case this doesn't tell you anything. The other issue that you can run into is that this limit could be very difficult to take, and it may not be obvious what to choose as your series for comparison. We then switched to some tests that dealt with series for both positive and series that have both positive and negative terms. So the first was the absolute value test. Essentially, we can determine whether or not this series converges by looking at the series of absolute values. So if that series of absolute values converges, then the original series has to converge. However, if this series of absolute values diverges, it does not tell us anything about the original series. It could converge or it could diverge. We don't know. We then looked at another test that works for a very special type of series that have both positive and negative terms called alternating series. And we saw that for alternating series, if the non-alternating part of the series is decreasing or non-increasing, and if the values of that are approaching zero, then the alternating series test tells us that that series does converge. Now, this is a great test. However, it only applies to alternating series. So again, it's sort of only applies to series of a very specific type. The last two tests we looked at were ratio and root test. So both of these allow us to look at some quantity that depends only on the series that you're looking at and analyze some limit. If that limit is less than 1, we get absolute convergence. If the limit is greater than 1 or infinite, we get divergence. But if the limit is equal to 1, it's inconclusive. So for the ratio test, you're looking at the limit as n goes to infinity of the absolute values of successive terms. So the absolute value of a sub n plus 1 over the absolute value of a sub n. If that limit is less than 1, you get absolute convergence. If that limit is greater than 1 or infinite, again, you get divergence. And if the limit is equal to 1, then the test is inconclusive. The series could either converge or diverge. Similarly, the root test, you look at the limit as n goes to infinity of the nth root of the absolute value of a sub n. If that limit is less than 1, you get absolute convergence. If that limit is greater than 1, or infinite, you get divergence. But if that limit is equal to 1, then again, the test is inconclusive. So all of this sort of raises the question, we have all these tests. When I'm looking at a series, how do I know which test to choose? Okay, so I tend to walk myself, and there's no one right process for thinking through this. As you practice more, you'll develop your own. But as I walk through this, the first question I usually ask myself when I'm looking at a series is it some sort of special series? So, for example, I might say, yes, it's a geometric series or it's a p-series, in which case, if it's one of those special types of series, then I have a nice special test for that, right? I have the geometric series test or I have the p-test that will very quickly tell me whether it converges or diverges. If, however, it's not a special series, then what I'm going to do is I'm immediately going to say, well, can I quickly rule this out by just looking at the limit of the terms? So I'm going to ask myself, what is the limit as n goes to infinity of the terms of my series? If that limit is not 0, right, then I immediately get that the series diverges by the divergence test, right, or the test for divergence, the nth term test. Okay. However, if that limit is equal to 0, then I still don't know. I have to sort of move on to some other test. The next question I'm going to ask myself is, okay, well, it's not any special series. The limit of the terms goes to 0. So now let's look at the series a little more closely. Does it only have positive terms? If it only has positive terms, then I have a number of tests at my disposal. I have the integral test. So if I look at that thing and go, oh, I could actually integrate that function, then I'll try integral test. But I might also look at it and say, well, this is a rational expression. I might quickly be able to compare it to like a p-series, in which case I would use limit comparison test. Or if that wasn't maybe quite as easy, I might switch to the regular comparison test or the direct comparison test to try and use some more sophisticated sorts of inequalities or comparisons to help me determine whether the series converges or diverges. If, however, those things fail, okay, so maybe I can't integrate it, or I can't quite find a limit or a series to compare it to, either via limit comparison or direct comparison, then I'll try switching to something like ratio test or root test, specifically if I see things like exponentials or factorials, which would be really helpful in those cases. Now, if my series does not just have positive terms, then I've got to ask some more questions. So the first is, I might ask, is the series alternating? If the series is alternating, then I'm probably going to first try the absolute value test. And then if the absolute value test fails, try the alternating series test. Now, the reason I might choose to do them in this order is if the absolute value test works, I now know that the series converges, and I know that it converges absolutely. However, if the absolute value test fails here, then I can go to the alternating series test. If the alternating series test gives me convergence, but the absolute value test did not, then I know that my series converges conditionally. However, if the alternating series test also fails, right, then I start to think, well, my series is probably actually just diverging. Now, if my series is not alternating, I only have one option. That's the absolute value test. So I need to try the absolute value test and see if that will give me anything. Now, if both of these fail, then I'll go to ratio and root tests. Specifically, if I see exponentials or factorials, that might indicate that one of those tests might be very helpful. Okay. And of course, you could ask, well, what if all of this fails? Well, it actually turns out there are many more tests for series convergence than we're going to cover in this course. So for example, earlier on, we looked at this series sine of n over n. It turns out that this series converges, but none of our tests would actually reveal that. There's another series convergence test called Dirichlet's test, which you can use to determine that this converges, but it requires a very delicate analysis. So we haven't given an exhaustive list of every possible series convergence test here. And even if you go to Wikipedia and search, you'll see there are many, many tests for convergence listed there. There are still series that won't be covered by any of those tests. And so what we hope to have presented here are sort of a sample of very useful tests that you can use. And if you ever needed to use another one, you now know how these sorts of things work. You could go to Wikipedia, look up a different convergence test, and apply it on your own.